Hi everyone, I'm excited today to officially introduce Rama. Last week, you got to see a taste of it when we released the Twitter scale Mastodon instance we built using Rama and posted a blog post doing a deep dive exploration of how it works. If you haven't read that yet, I highly recommend checking that out to see a complete example of how Rama reduces the cost of building end-to-end scalable backends by 100x. Today, I'm going to give a tour of some of the things that make Rama so unique and so powerful. It took us 10 years to design and build Rama, so needless to say, there's some mind-bending stuff in here. I'll start by recapping the programming model of Rama, which we showed in our post last week, and then we'll explore the topics listed here. You'll see how Rama doesn't just reduce the cost of implementing an application, but with its deployment and monitoring features also reduces the cost of getting an application into production. This is what we mean when we say Rama is for building applications end to end. Let's quickly summarize the programming model of Rama. The programming model itself isn't new. What makes Rama so powerful is how much it integrates and generalizes each of these pieces. On the left are depots. These are distributed, durable, and replicated logs of data. If you're familiar with Apache Kafka, depots are very similar except integrated with the rest of Rama. Next are ETLs, extract, transform, load topologies. These consume data from depots in parallel to produce indexes, which we call partition states. Most of the time spent building Rama applications is spent programming ETLs, which are programmed with a pure Java API. Next are partition states, which we usually refer to as p-states. P-states are how data is indexed in Rama, and they're also durable and replicated. They serve the same purpose that databases do, but they're much, much more powerful. I talked about this a lot in my post last week, and we're going to look at them a lot more in this video. The last concept in Rama is queries. There are two forms of queries in Rama. The first is ad hoc queries that can retrieve or aggregate data from one partition of one p-state. These are called point queries. The second are query topologies, which are predefined queries that can look at any or all of your p-states and any or all of the partitions of your p-states. They're real-time, on-demand, distributed computations programmed with the exact same Java API as used to program ETLs. This is a module. A module is how all these concepts are packaged together into a Rama application that you then deploy onto a Rama cluster. A module is an arbitrary collection of depots, ETLs, p-states, and query topologies. Here you can see this module has two depots, one ETL, two p-states, and one query topology. Our largest module in Mastodon has 14 depots, 5 ETLs, 33 p-states, and 16 query topologies. So that's the high-level overview of what Rama is. Let's dig into some of what makes it so powerful, starting with p-states. P-states do in Rama what databases do in traditional architectures, and you can understand p-states in contrast to databases. When you look at databases, they all have fixed indexing models, what they call data models. There's key value, document, column-oriented, graph, and so on. A better way to think about indexing is in terms of data structures. A data model is just a specific combination of data structures. Key value is just a map, a document data model is a map of maps, column-oriented is a map of sorted maps, and so on. Databases that support secondary indexing just materialize additional maps alongside the primary data structure. A database like Redis is a little more flexible, allowing your values to be sets or lists. But ultimately, all these databases and their underlying data models support a very small number of data structure combinations. We're talking about just a handful versus the infinite number that are possible. Building backends has always been like this, at least since I've been alive. So it can be hard to see this as a limitation. But this is like if in regular programming, you could only use a handful of data structure combinations and nothing else. That would be extremely restrictive and make you twist yourself into knots trying to get things to fit together. But this is the reality of backend development from databases being so restrictive. If you can't fit a use case onto your database's data model, then you need to deploy another database with another data model. Deploying and maintaining multiple databases is expensive. If no database's data model fits your needs, then you might need to make your own database from scratch, which is extremely expensive and unfortunately not that uncommon. Rama's p-states are completely different. Every p-state you create can be whatever data structure combination you want, and you create as many p-states as you need to support all your use cases. P-states have a feature called subindexing, which allows you to represent nested data structures with millions or hundreds of millions of elements efficiently. Let's look at a few examples. Here's a p-state that's just a map, which is the same as a key-value data model. Here's a p-state that's a map of maps, which is the same as a document data model. In this p-state, the nested maps have explicit keys and a different schema for each key. Here's a map of subindex maps, which is the same as a column-oriented data model. Here's a p-state that's a map of subindex lists of maps of subindex sets, which doesn't correspond to any existing data model. You can see it's completely trivial to match any data model with p-states, and there's infinitely more combinations of data structures you can make. With data structures, you can shape your indexes to perfectly meet your application's needs. It's extremely efficient, and because it matches your application's use cases exactly, there are no impedance mismatches. Our Mastodon implementation is a great example of this, with great variety in the optimal data structure shape for each use case. Ultimately, the combinatorial possibilities of data structures makes them infinitely better than data models, and this is one of the key reasons Rama is so powerful. With such a flexible indexing model, you might be wondering how p-states are read and written to. Rama's mechanism for this is called paths, and paths let you slice and dice your way through a p-state extremely concisely, no matter how complicated its structure. Since p-states are just data structures, we can play with paths with normal data structures outside the context of a module. Here's some Java code making a map of maps of lists. You can visualize this data structure like so. Now let's run some queries on it from a groovy REPL launched from the open source Rama examples project. Here I'll grab and print the value from within one of the nested lists. Paths are composed of what are called navigators, and here I first navigate to the value for key A0, then the value for key A1, then the value of index 1 in the list. This dataflow code binds navigated values to the variable v, and then it prints that variable via the call to print line. This query produces the value 3. You can visualize the navigation like this. A good way to visualize how paths work is as hopping through a data structure, step by step. Here we hop to the nested map, then we hop to the nested list, then we hop to the value inside the list. Let's look at another example that navigates to multiple values. Here I'll navigate to every value in every list in the map for key A0. You can see this prints many values. This path can be visualized like this. That map vals navigator goes to every value of the map, and that all navigator goes to every value in each list. Let's look at another example that includes filtering. Here I'll do the same path as last time, except only navigate to values that are less than 7. From the output, you can see it filtered out all values greater than or equal to 7. Here's a visualization of this path, with the only difference being that additional filtering step. From these examples, you can get the general sense of how paths work. The collection of navigators provided by Rama each perform one very specific navigation, and then you compose them together to precisely target the values you care about inside an arbitrarily complicated data structure. Because it's a composable abstraction, the possibilities are endless. Let's look at one more example. Let's do the same navigation as last time, except this time omit the sum of the navigated values. The subselect navigator puts all the navigated values into a list, and the view navigator transforms that list with the provided function, which sums the values. You can use any Java function there, not just the built-in ones. When you execute paths like these on p-states, the paths execute completely server-side, so paths like these that aggregate values are very efficient. Now this is barely scratching the surface on paths, but even with just these few navigators I showed, you can get a lot of work done, but there's so much more that you can do with paths. This page right here from the Rama documentation goes over all the intricacies of paths in detail. Let's take a look at another part of Rama, its dataflow API for coding ETLs and query topologies. This API is one of the major breakthroughs of Rama. Rama's dataflow API has the same capabilities of a general-purpose programming language, while also being able to seamlessly distribute computation across a cluster of nodes. I'll give a quick tour of it to show what I mean. As you saw before, the dataflow API can be used outside the context of modules. Most of the API is available in this context. The only parts that are unavailable are those that have to do with moving computation around a cluster. Playing with it in this context is a great way to learn through experimentation. Let's take a look at an example. This code processes every number within a list, multiplies each number by 10, and then prints the result for each number. Dataflow code operates fundamentally differently than a regular language like Java or Python. In those languages, the flow is call and response. You call a function, and it returns a single result back. In dataflow, on the other hand, operations receive input and emit values to subsequent operations downstream. Operations can emit 0 values, 1 value, or many values, and their outputs can be consumed by more than one downstream operation. This example starts off by calling explode on the provided list, and it binds emitted values to the variable v. The explode operation binds that variable one time for every element in the list. V here is a variable just like in any other programming language. It has a scope and can be passed around to other operations. Variables in Rama are strings that begin with the star character. The next operation, which runs the times function, executes for each emission from the previous operation. In this case, it runs 4 times, once for every value emitted by the explode operation. This operation multiplies each number by 10 and binds the result to v2. Unlike explode, times always emits exactly one output. The next line uses the printline operation to print the results. Note that the arguments are a mixture of constants and variables, just like you're used to doing in regular programming. Finally, the execute call compiles the dataflow code and runs it by sending a single empty input at the root of the dataflow graph. This causes the expected results to be printed. The execute function isn't used when programming modules, as Rama takes care of compiling and executing dataflow code when deployed to a cluster. It's only used when playing around outside the context of a module like this. Dataflow code gets compiled to efficient bytecode when deployed in a module. So variables like you see here become actual variables in the compiled bytecode, and the efficiency of dataflow code is as good as compiled Java. Let's take a look at another example. This is the same as the previous one, except instead of using explode, I'll use explode indexed. Explode indexed emits 2 fields, with the first being the index of the value in the list. This index is bound to the variable I and printed with the results. So not only can operations emit multiple times, they can also emit multiple fields per emit. Next, let's take a look at an example of using a conditional in dataflow code. The first argument, if true, is either true or false and determines which block gets executed. You can pass a variable there directly, but in this code, I pass an expression that evaluates to true or false depending on whether the value is even or odd. When true, the first block gets run, and when false, the second gets run. The next line after the conditional runs whether the expression was true or false. You can think of that line as attaching to both the then branch and the else branch. Merging branches like this is called unification, and you'll see how you can do this explicitly in a later example. There's also something interesting going on here with the stir variable. Variables are in scope after unification only if it's defined on all parent branches. Since stir is defined in both the then and else blocks of the conditional, it's in scope after the conditional. Let's take a look at another example that uses a loop. Loops in Rama accomplish the same thing as loops in a language like Java, though the definitions are quite different. With Rama loops, you explicitly continue iterations of a loop, and you explicitly emit from the loop to invoke code defined after the loop. This code prints every power of 3 less than 100. The loop is defined with the variable total that has an initial value of 1, and this variable is updated for each iteration of the loop. If total is less than 100, then it's emitted from the loop. Note that the code attached to the emit is invoked immediately, before the continue loop call happens. The emitted value is bound to the variable v, and then printed via that call to print line. When that code finishes, the continue loop line runs and the next iteration of the loop begins. For the next example, let's take a look at how you can control the dataflow graph to create branches and merges. The primitives that Rama provides for this are called anchor and hook. Anchor names a location in the dataflow graph. Here, the first anchor is called root. The following code defines the first branch of code, which increments every value and binds the result to the variable v2. It then names the end of this branch, branch 1. The next block of code uses the hook operation to change where the subsequent code attaches. Instead of attaching to the end of the previous code block, It instead attaches to the root anchor, creating another branch. This code multiplies each value by 100 to also bind the variable v2. Note that this v2 has nothing to do with the other v2 since they're on separate branches. The unify call merges the two branches together. Any values emitted from either branch causes that code after the unify to execute. Just like you saw with conditionals, variables that are defined in all parent branches are in scope after the unify, so v2 is in scope here. If a variable was defined in one branch but not the other, it would not be in scope after the unify, and you would get a compilation error if you tried to reference it. Here's an example showing how easy it is to intermix Java code with your dataflow code. I can't do this one at the Groovy shell since it can't do Java lambdas, so I'll show it in this slide instead. The first line re-implements the built-in explode operation with custom Java code. It iterates over the list and emits each value individually. The next line runs a Java function that produces a string from an integer input and a string input. You can see here you can inject arbitrary code with or without an output collector. With an output collector, emits are done explicitly. Without an output collector, Rama takes care of emitting the return value of the function for you. Injecting Java like this into dataflow code is extremely common, and Rama makes it as convenient as possible. You can assign types to the input arguments however you want, and you can also inject Java code through Java method references or by making a class that implements Rama's interface for custom operations. As you've seen already, Rama provides a lot of built-in operations in its ops class. These include arithmetic operations, comparators, and other utility functions. Now let's take a look at the heart of distributed programming with Rama, partitioners. A partitioner is an operation that relocates computation to another partition of the module. Partitions of a module are called tasks. The line before and after a partitioner can execute on different tasks on different machines, and Rama takes care of all serialization and network transfer to move the computation. This module is contrived, but it demonstrates a few things about partitioners. This module has one p-state that stores a single integer per partition. It consumes a depot that receives either numbers or null. If it receives null, it uses all partition to run the subsequent computation on every task, incrementing the number on each p-state partition by 1. If it receives a number, it uses hash partition to choose a task for that number. Hash partition hashes the provided value and mods it by the number of tasks to choose the target task. Because it uses a hash function, it evenly distributes keys among all tasks while also ensuring the same key always goes to the same task. In this case, it adds the number to the total stored on the p-state partition on that task. The module prints updated values and their task ID for each update. Let's see it in action. In this Groovy shell, I have the module launched and running already and a client to the depot already open. When I append 95 to the depot, you can see that updated the value on task 3. When I append 95 again, it updates the value on the same task. When I append 96, it goes to a different task, and when I append 97, it goes to another task again. 98 goes to the same task as the last one, and 99 goes to the last remaining task. When I append null, you can see there's an update on all partitions. Since the updates are happening in parallel, the order of the print lines is random. You can see each append I do of null has a different ordering. From this example, you can see how partitioners compose seamlessly with other dataflow code, in this case being used within a conditional. You can also use partitioners within loops, allowing you to have looping computations that span many tasks. Rama has a few other built-in partitioners, and you can also define custom partitioners yourself that compute target partitions based on some input data. I only scratched the surface here on what you can do with the dataflow API. With the examples I've shown, I've tried to demonstrate what I mean when I say it has the same computation capabilities of a regular programming language. If I had to summarize what makes the API so powerful, it's that it gives you total control over running whatever computation you want on whatever partitions it needs to be running at any point. I do want to point out a few other parts of the dataflow API that I don't have time to cover in this video. This part of the documentation covers batch blocks, which are a feature of the dataflow API that has the same capabilities as relational languages. Batch blocks can do inner joins, outer joins, aggregations, and subqueries, but expressed in a different way than you would with SQL. This section of the docs is further down on the same page and covers macros. Macros let you define dataflow code that expands to other dataflow code, letting you reuse chunks of dataflow code. This is a really useful facility, and it's something we made use of heavily in our Mastodon implementation. Let's switch gears and look at another part of Rama that makes it so unique and powerful, the way it co-locates computation and storage. We looked before at how modules are deployed as many worker processes across a cluster. The workers share responsibility equally for all computation and storage within the module. This means each worker process hosts a subset of partitions of all depots and p-states, as well as executing its fair share of ETL code. In this image, you can see what workers look like internally. Partitions of both computation and storage are organized on what are called task threads. Here you can see this module has 2 task threads per worker, with each task thread having a partition of each depot and p-state. Each task thread also has a queue that processes events that run on that thread. Those events span everything that Rama does: running ETL code, running p-state queries, running query topologies, collecting telemetry, as well as other internal system events. Each task thread has exclusive access to the depot and p-state partitions hosted on it. That is, you can't access a depot or p-state partition from another thread and can only do it via running an event on that thread. So when you look at code like this, the code is always executing on a task thread. When you reference the p-state in dataflow code, you're always referencing the partition of the p-state that's local on your task. While your event is running, nothing else can read or write from those partitions. This lets you do some really powerful things like update multiple p-states within a single event, and then readers of those p-states will see all those changes atomically. It's impossible to see only just one of those p-states updated. Likewise, you can read from multiple p-states in one event and be guaranteed nothing else wrote to those p-states in between. When you want to look at data from another partition, you use one of the partitioner operations you saw before to switch to a different partition. This colocation is also really efficient. Reads and writes are local operations, so you don't have to do a network round trip for every operation like you do with a database. You have to do a network operation to get to the right task, but once you're there, you can do as many reads and writes as you want. Colocation also enables Rama to be extremely efficient by batching together writes for multiple p-states to replicate and persist them together. In our Mastodon implementation we showed last week, a big reason why the performance numbers are so strong and the implementation so concise is because of how Rama co-locates computation and storage and how the implementation takes advantage of that. Next, let's take a look at how Rama greatly simplifies deployment and operations. Up until now, building deployments has been a complex engineering challenge of its own. You have to coordinate resources for potentially dozens of systems, and updating an application can be a complex orchestration process. It's not uncommon for deployment engineering to involve entire teams writing hundreds of thousands or millions of lines of code and configuration. That's a massive amount of extra cost in addition to building and testing the actual product code. Rama being such a general purpose platform changes this story completely. Because Rama is so general purpose, able to build entire backends end to end, its built-in deployment operations either eliminate or greatly reduce the need for deployment engineering. You can say goodbye to piles and piles of shell scripts. There are 3 operations that Rama implements for deployment: deploying a new module, updating an existing module to change or add functionality, and scaling an existing module either up or down. Each of these is just a one-liner at the terminal. Let's take a look at an example. Here I have a module that has a single query topology that computes the nth Fibonacci number. The query topology implements this recursively, which you can see here. The base case returns 1 for the first 2 numbers, and it uses recursion for subsequent numbers. You can implement this much more efficiently, of course. I'm just doing it this way for demonstration. Let's actually modify this implementation to put in a bug to return 2 for the base case. Then we'll fix it later by doing a module update. Now at the terminal, I'll build a jar and then deploy the module. When you deploy a module, you tell it how much parallelism and replication you want. I'll run this with 8 tasks, which is Rama's name for a partition, 4 threads, 2 workers, and a replication factor of 2. Now I'm going to connect to my module in a Groovy shell and run the query topology. First, I'll tell it where the conductor is located by creating a config map. Then I'll connect to the cluster using the Rama Cluster Manager class. With this object, I can fetch a handle to my query topology, like so. You can see when I execute it on the base cases, I get 2 back. And because of that, the answer is wrong for subsequent indexes as well. Let's now fix the module by fixing the base case. Now I'll go back to the terminal, build a new jar, and do a module update. You can see this is an even shorter one-liner than to deploy. Rama's implementation of module update carefully coordinates the handoff of responsibilities between the old and new module versions to smoothly transition reads and writes. It's also completely fault tolerant and does the right thing even in the presence of absolute chaos on the cluster, like machines dying or the network partitioning. Back to our REPL, we can execute the query topology again. Note that I didn't recreate a new connection to the cluster or query topology. I'm using the same instance I was using before the module update. Now when I run the query topology, it returns the correct answers. Clients to module objects automatically transition themselves to the new module version, which is true for depot and pstate clients as well. Scaling works just like module update, except instead of giving Rama a new jar, you give the module new parallelism settings. Let's see an example by doubling the number of workers for this module. And that's all there is to it. Let's switch gears again and take a look at the built-in monitoring Rama provides for all modules. Here in the cluster UI is a list of all modules on the cluster. You can see the module at the bottom is called monitoring. This is Rama's implementation of monitoring, which is a module just like all the others. It has a depot that workers from other modules append to once a minute with aggregated telemetry data. When I click through into a module, you can see a list of all the depots, topologies, and pstates for the module. Down below, there's telemetry on the module as a whole. Here's the distribution of loads on task threads. Here's a breakdown of the number of events being processed across all task threads. They're broken down into a tree of categories, and you can look at any level of that hierarchy. Likewise, there's a similar chart below for event timings. All events are categorized, counted, and timed, not only events for module code, but internal system events as well. Scrolling down, you can see there's a lot more information, including telemetry on replication, queue sizes, and garbage collection. You can zoom out by changing the time granularity here. From here, I can zoom in to look at an older time range in more detail. Here's a page for a microbatch topology. Here you can see telemetry on how long each microbatch is taking, how big each microbatch is, and a breakdown of how long each phase of a microbatch takes. Below is a progress graph showing how up-to-date the topology is on each depot it's consuming. When your cluster is adequately provisioned like this one, the progress and depot lines are on top of each other. Here's a page for a pstate. This shows how many reads and writes are happening on the pstate and the distribution of times for those reads and writes. I'm only scratching the surface on what's available here. Every depot, pstate, and topology has detailed telemetry, and you can look at telemetry on a worker-by-worker basis as well. All this telemetry helps a great deal in understanding the performance of a module in production, diagnosing issues, and determining when to scale. Another part of Rama I'd like to point out is Rama's integration API. As we've shown in our Twitter scale Mastodon implementation, Rama can build end-to-end backends on its own. But that doesn't mean it has to be used that way. We've designed Rama so it can integrate seamlessly with other tools, whether databases, queue systems, monitoring tools, or anything else. This allows Rama to be incrementally introduced into an existing architecture. I won't go into detail on the integration API in this video, but to learn more, you can visit this page from the Rama documentation. To see an example of using the integration API to integrate Rama with another system, you can check out the open source Rama Kafka project on our GitHub, which enables Rama to use Kafka as a depot in ETL topologies or to write records to Kafka from an ETL. Rama is available to try for yourself right now. We've released a build of Rama which exposes the full Rama API for use with simulated in-process clusters. You can use this to run the examples you've seen in this video, as well as our Mastodon implementation when we open source it next week. Soon, we'll be announcing a private beta to give companies access to the full version of Rama, which runs as a distributed cluster. On this page from our documentation called Downloads, Maven, and Local Development, you can find the details of how to include this build of Rama as a Maven dependency in your projects. I've already referenced the documentation multiple times, and I'd like to point it out once again. We've spent a lot of time writing high-quality documentation for Rama, and that's the best way to learn the ins and outs of using it. At this link, you'll find a collection of tutorials, guides, and reference documentation. We recommend starting with the 6-part tutorial that culminates in building a scalable social network from scratch in only 180 lines of code. You can also find the complete Java doc for the Rama API on our website at this link. As you learn Rama, you'll find it not only scales to handle whatever load your application will face in the future, but it's also the fastest tool for building the first version of your application. Rama has a learning curve, but you'll find it well worth your time. Finally, you can keep track of Rama development as well as announcements of our upcoming private beta through these resources: our Twitter account, our newsletter, which you can sign up for on our website, and the Rama user Google group, where you can discuss Rama or ask questions. Thanks for watching.